and let me recall that divisor class group for P1 times P1 blow it up in 8 point is 10-dimensional with the following generators, and intersection form, non-trivial intersection forms are as follows. 1 ei squared equals to -1. So we discussed last time. Well, for what this is could be useful, namely for calculating Backlund transformations of the Painlevé 4 equation, which I hope will be done today. Now I'm not sure that we will start about Q case today. I'm sorry, but during my preparation, I understood that there is a lot of material. So, and also, as you remember, we have the following space of initial data for Painlevé 4. So here we have two blow-ups, yes, and here we have 4. So we have 1, 2, 3, 4. Well, so this blow-up we call E2. So this divisor is E1 minus E2. This one is H2 minus E1 minus E5. This one is E5 minus E6. This one E6 minus E7. This one E7 minus E8. And this one is E8. This one is H1 minus E5, E3 minus E5. This is E3 minus E4. And this is E4. So, what are they? So they're just they're not important for the structure. So I can draw it, but it will be like H1 minus E1, H2 minus E3. So you should remember that for our structure, so we take P1 times P1, blow up it in 8 points in the following way, and also it is important to remove this these lines which is in bold, so they are inaccessible.
So you do always the blow up of 8 points, but what changes among the different Painlevé is the configuration.
Is the configuration, yes, of these bold lines. Yes, so here, so all these bold lines have a self-intersection -2. So in fact, I will write in bold lines with self-intersection -2, and in this way with self-intersection -1. And with other self-intersections, I will try not to.
Maybe you can use color if there is just there is not.
No. So yes. So inside the Picard lattice, we have sublattice E61, affine E6. So here we have so the imaginary root of this E61. What should we do? We should take this roots with multiplicity 1, this with multiplicity 2, this and this with multiplicity 3. So, and if we sum all these roots, we'll obtain the following. And below we will see that this delta corresponds to anti-canonical class, which is by definition the class of the volume 4. Okay. So let's okay, so let's prepare to work with these divisors. So which divisor corresponds to the to the curve. If we take for example some divisor, some curve of the form like don't know how to start. So let me think. Let me think. Well, so if we have divisor of such form, what we can say about it? We see that it intersects with any line. So if we are not speaking about blow-ups, only about the first part, d1h1 plus d2h2, we see that it intersects with h2 line in d1 points and with h1 line in d2 points. So it's a curve of b degree d1 d2. So this means that the highest power of f of p, sorry, the highest power of Q is D1. Yes. And the highest power of P is D2. And when we add this MI with sign minus, this means that this
So the Q and P are the Hamiltonian variables.
Q and P, yes, Q and P is a variable as initially the canonical variables, but now they are coordinates of P1 times P1. So it is P equals to infinity, it's P equals to 0, it's Q equals to 0, and it is Q equals to infinity. So
You're thinking about the divisors realized as an algebraic curve,
yes,
and that there is an equation.
yes, yes,
For that.
yes. So we have an equation. I explained how the divisor corresponds to the to such curve which is given by an algebraic equation.
Yes.
So
Remind in which space is the algebraic equation realized? Really, P1 plus P1, right?
yes, yes. Initially it's P1 cross P1, and yes, and if we add some MIs, EIs, this means that this curve intersect EI point EI in MI point with MI times. Yes. So so then we can calculate the dimension of curves which correspond to such divisor. So what can we do? So the dimension arising from P1 times P1 is as follows. Why? Because you have powers from 0 to D1 over P, from 0 to D2 over Q, or conversely. So and you should remove one coefficient, which is just the coefficient of proportionality. Yes. So so this will be dimension of this curve in P1 times P1. After the blow up, we have several conditions. I mean that there are a manifold of cars which correspond to the given divisor. For example, yes, yes. So -1 is like a productivization. Yes. So because we should because, for example, we obtain some we can work with some transformations at the level of Picard lattice, and then we can restore the coordinates using these transformations. And to do that, we should know, for example, that the dimension, for example, is 1 or 0 or something like that. And we will do it today in the most common case. So so what happens if we have an isolated blow up then it means and the curve passes through it. We have one condition, yes, then that in this point the equation is satisfied, yes. When we have more, when the curve passes several times through the point. So here is some neighborhood. Yes, for example, here. So let's see what happens if we write this curve in the neighborhood of this point. For example, let's move coordinates at this point will be 0, 0. Okay. So in coordinate where this point is 0, 0, so we have some C EJ, PI, QI, PJ, E runs from 0 and G runs from 0 to D1, D2. Yes. So we have a relation that the curve passes through this point one time. It's just C0, 0 equal to 0. Yes. Well, and in this case, in the neighborhood, we have a relation like this: C01P plus C10Q equal to 0. So we see that that only one curve with certain equation passes through this point. To obtain several curves, we should also remove these two coefficients. Yes, then we will obtain. Then the leading order will be quadratic. Yes, and we will obtain two curves which pass through the point. So so if we have m1 equal to m equal to 1, we have one condition. When we have m equal to 2, we have 1 plus 2 conditions. When we have m equal to 3, we have 1 plus 2 plus 3 conditions, etc. Because at the next point we should vanish the quadratic order. Yes, to obtain some cubic point.
This is the number of times the curve passes through.
Yes. So finally, this means that the dimension in case of isolated, for example, of isolated blow up is as follows. But it's of course always satisfied. Yes. M plus 1 over 2 because we have arithmetic progression. Yes. So E from 1 to 8. So example. Isolated blocks.
Components in general position, right?
Yes, isolated. For isolated blow-ups, yes. E1, E2, E3, E4.
But should there be some condition that they do not lie on one line or something like that?
So you speak that, for example, they are isolated, but they lie on one line. Yes.
Well, they need to find somewhere.
Line, horizontal or vertical, of course. This means because for P1 times P1 we have some special divisors. Yes, H1 and H2.
So if we take, for example, three points corresponding to the special divisor and place them on one line,
probably can change this dimension or not. Because if some line passes through two of these points, then it necessarily passes through the third one. And if they're in general position,
yes. That's a good question. So yes, I understand. So this is a good question, and now in the example, we will see how this formula can fail. Yes. So for example, so zero example is for example case divisor H1. Yes. So we have the dimension of class H1 is equal to 1. Yes, this is just pencil of vertical lines. Okay, so also this could be rewritten in a more short way. So let's denote this as lambda. Yes, and we can write it as lambda time intersects with delta plus lambda over half. Well, let's see. Let's take the cars with self-intersection -1 and which have lambda times delta equal to 1. Yes, we obtain the dimension will be equal to 0. For example, this is H1 minus I. Yes. So we take the only line which passes through E. Yes, and also this formula holds any of them, and also this formula gives dimension 0 also for just EI. Nevertheless, that it is not, the formula is not by design for this case, but the answer is also true. Well, and if we take lambda times lambda equal to -2 and lambda times delta equal to 0, which is just about our root system, yes? We obtain that the dimension is surprisingly -1. What does this mean? This means that this could be understood that we have an extra condition on the positions of the blow-ups. For example, here we have H2 minus E1 minus E5. We can draw such line only in the case when E1 and E5 have the same coordinate P. Yes, and that's true. It's infinity. So of course, if we have some conditions, then the dimension of could fall to a negative number or differ from this naive calculation. Pasha, are you satisfied? Okay. Okay, so and now we will use all this stuff to obtain formulas, to obtain all Backlund transformations of our Painlevé 4 equation. So I will start but I will start from describing from describing this relation. So for P1 times P1, we can take volume form, for example, as follows. Very simple. And you can see that its class is minus 2H1 minus 2H2. Yes? Sorry. Thank you. Because I work only with Painlevé equations, I always try to make such mistakes. Okay, so the divisor is minus 2H1 minus 2H2. That's because of these lines, yes? Because when we change the variables to Q to Q minus 1, P to P minus 1, we have poles of order 2 in infinity, yes? It is D 1 over Q wedge D 1 over P divided by 1 over Q square, 1 over P square. And you can ask why we take this form. Maybe we can take some another form multiplied by some function of Q and P. But if you do such a thing, it could be easily understood that nothing changes. So the class will be minus 2H1 minus 2H2. So because that's because of the properties of meromorphic functions. Here, namely, some irrational functions. So, for example, I don't want to spend time to prove it, but for example, if you write, I don't know, dq times dp over, I don't know, pq minus 1, yes, what happens? After change of variables, it goes to dq times dp. Here we have p squared q squared, p minus 1 q minus 1 minus 1, which is equal to pq, pq minus 1 with minus dq dp. So what we have? We have that in both maps we have such pole, yes, and also in the map of infinity we have minus h1 minus h2. And what happens when we go to when we blow up our space? So example, what happens? Well, for example, I want to blow up point 1, 1. So, and I will take coordinates q tilde equal to q, p tilde equal to q minus 1. Sorry, q tilde minus 1, p tilde minus 1. Oh, yes. So what I will have conversely, well, sorry, p minus 1, q minus 1. So here I have p tilde q tilde plus 1 equal to p. So my form becomes q tilde dp tilde dq tilde. Yes. So in this map, locally I obtain 0 in the point where q0 is 0, which corresponds to the point q, which corresponds to the point 1, 1 after blow down. So I obtain, so after the blow up, I obtain a new 0, just on the exceptional divisor. So after the blow up, I will obtain minus 2h1 minus 2h2 plus e. So and after 8 blow-ups, I will obtain this one with inverted sign. That's why here I write minus k, anti-canonical class. Okay, so let's take our Picard lattice and let's take inside our Picard lattice the following subspace of lambda. Yes. So so it appears that this subspace is non-dimensional, and it is root lattice of E8. E1 minus E2, H1 minus H2, H2 minus E1 minus E2, E2 minus E3, E3 minus E4, E4 minus E5, E5 minus E6, E6 minus E7, E7 minus E8. So this is so I don't know in which field we take Picard lattice, maybe in integer field. So I think we obtain integer root lattice without any multiplicities. Okay, so and inside this root lattice, yes, we know that we have E61 of our inaccessible divisors. So if we have no inaccessible divisors, then of course we can make So so if we take our space and make some transformation, it will lead to some transformation in Picard lattice, and of course some transformation of this E81. Yes, because it is defined in an invariant way.
How do you choose the basis of divisions that you assign to each node? Why those linear combinations?
So I have some under this condition I have some lattice, and then I find that this lattice is E81.
You mean that you solve that condition and then you write the diagram according to the intersection between the various divisions. So that
Yes,
you choose
yes.
as a basis of the
Yes. So this is rather, in fact, rather a hard calculation, which is better to do with mathematics. And now we will also calculate some root lattice, and we will do it by hands. It will be simple. Okay, so if we have some transformation of our space of initial conditions, it will be some transformation of this E81, of this root system. So each transformation should lead to some a fine extended Weyl group of this E81. Yes, but we also know that we cannot move this. We cannot change this root lattice, this root sublattice. It should be invariant.
that is a specific to Painlevé.
Yes, and this is already specific for Painlevé 4. So when we are speaking about the most general case, like Q Painlevé E0, which has only one component of minus two curves, then nothing. Then we have no conditions and all. And we have all the symmetries. Okay, so let's calculate. Orthogonal subspace to this E61 in E81. Yes. What is its dimension? Yes. What is the rank of the subspace? What do you think? E61 inside E81. So we want to find E61 orthogonal in E81. And what is the rank? No. Another direction. So the rank is 3 because our form is not Euclidean. We have delta which lies everywhere. Yes, because it's orthogonal to itself. Okay, so the rank is 3. So let's calculate. It's very easy. We should take D1, D2 minus M1 E1 minus M8 E8, and let's see what means orthogonality to all the generators. So what means orthogonality to this one, H1 minus H2? Opposite. Why opposite? The same. Yes. So this is this relation. So here we have relation that d1 equal to m1 plus m2. Correct? Yes. Yes. Or sum equal to 0. Sorry. Why d2? No. Sum, yes?
Are you doing now? Are you preparing to be 8?
Yeah. Sorry. Yes. Yes. Very good, Pasha. Yes. Of course, I will now obtain only delta. Thank you. Yes, we should look here. Thank you. Okay. So what we have? We have that. Yes. Lambda was okay. 1h1 plus d2h2 minus m1e1, etc. minus m8e8. So let's see. What does this mean? This, and this. Yes, and also this. Yes, so we have that m1 equal to m2, and also m3 equal to m4, and m5 equal to m6 equal to m7 equal to m8. Well, very good. So, and we have now we have only two conditions. First condition says that d2 plus m3 plus m5 equal to 0, and d1 plus m1 plus m5 equal to 0. Well, so so finally, let's express this divisor in terms of m1, m3, and m5. Yes. So what we have? We have, so d1 is minus m3 minus m5 h1. No. Plus minus m3 minus m5 h2. Well, minus m1 e1 plus a2 e2 minus m3 e3 plus a4 minus m5 e5 6 7. Sorry?
So you kept M1 and 3 and then 5.
Yes.
Yes.
Yes, I mean, for simplicity, I denote this by sum. Okay. So, and now we should find here, yes, now we should find here the roots. I'm afraid that is there d2 plus m3 plus m5? No. No, minus. Yes? Because we have three minuses. 1, 2, and 3 from self-intersection. Yes? Yes. So finally, what we see? We see that we have H1 minus E1 minus E2 with coefficient M1. Yes. We have M3 with coefficient H2 minus E3 minus E4. And we have coefficient M5 with H1 plus H2 minus E5, 6, 7, 8. So we find the generators in this lattice, and we found it in such manner that that this is also root of some lattice. Yes, and this lattice is A21.
So delta is the sum of them, no?
Yes. So now how to find the symmetry of equation? When we have such transformation, we have a transformation in E8 such that orthogonal lattice as a whole remains the same. So this means that from on Sx1 we can have only aptomorphisms which rotated. Yes, and uh, uh, we have so how to say. Mm. So this lattice which we obtained it if we take only transformations which preserve E61, then this lattice A21 is defined also in an invariant way. Yes. So this means that each symmetry leads to a symmetry of this lattice. So and the whole space and the whole symmetry group is a fine extended A2. So it's generated by reflections in these three roots, and also we can take outer automorphism of Dynkin diagonal. Yes, this is like S3. Yes. So in fact, there is no guarantee that all of these transformations really exist. So this is like so we find that each backward transformation leads to some transformation inside this group. Yes, but the opposite in general is not true. Here it's true, and even more, because we will see that we will find that there are some transformations, symmetry transformations, which act trivially on the Picard group. They could be classified in a very simple manner, so it's not a problem. And it's an issue of a very degenerate equation. So, for example, for Q Painlevé 6 and most Q Painlevés, there are no such peculiarity.
Are you assuming that if we have some transformation that preserves the symmetry lattice together with the quadratic form, then this transformation is necessarily described as some element of this fine extended vector?
Yes, Yes, because the root system, if we have a root lattice, the root system can be found in the root lattice very simply. It's just all the elements of length minus 2.
In this particular case.
So how to say it? So here I think it's important that we have a lattice, the orthogonal lattice, which is calculated in integer numbers.
But what do you mean by extended?
Extended. This means that we take all the automorphisms of the Dynkin diagram. So to be more rigorously, one should write EE, not just E. There are the whole group of outer automorphisms of Dynkin diagram is a group of transformations of automorphism of finite diagram plus automorphisms of a finite diagram.
So in this case, there
is a rotation and also reflection. Yes. Yes. So Pasha, are you satisfied about the logic about the symmetry?
Well, maybe in this particular case it works. In the non-simplification to this case, for example, if it fails,
Yes, of course, but for Painlevé there are no simplest cases. Not simplest cases.
Yes, and I also I'm not sure
about other series D.
Yes, it's true that all vectors in normalized have
So I think that is true. I asked Misha this sometime, and he said me that this is true.
So it's just true. You're saying that any morphism maps on this neural system to itself.
Yes.
And any such map, well, obviously it should be something known, but we should know that any such homomorphism is given by some element of the finite standard.
Yes, that's also true. Yes. So. Well, let's calculate. I have minus 3 minutes. Let's calculate. Let's start to calculate the symmetry. For example, a simple reflection. So, for example, we take reflection H1 minus this reflection. It acts as follows. H1 goes to H1, and H2 goes to H2 minus, H2 plus H1 minus E1 minus E2. Yes? And also E1 goes to H1 minus E2, and E2 goes to H2 minus E1. And other transformations are trivial. We can also remove this because it's trivial. Well, how we can find the coordinate transformation from this Picard transformation? We see that so for example we have such one-dimensional pencil like P equal to some P0 in the pre-image. Yes. Then after the transformation, we will obtain some birational expression like P0 equal to numerator and denominator. So we will obtain some curve like of the form n minus P0d equal to 0. And we know what is the curve we have. We have a curve of B degree 1, 1, which goes through E1 and E2. In this case, it means that it goes only from it. So it goes from this to this point, but not in any point, but in point where we blow up E2. Yes, because it's orthogonal to the first exception divisor E1 minus E2. So let's see what we have. So curve of B degree 1 could be written as follows. What we have, we should take P. We should change the coordinates. So we have P minus 1, P minus 1. Yes, so this means alpha Q plus beta plus gamma PQ plus delta P equal to 0 in point 0, 0 in new coordinates. So B is equal to 0. This is one condition, that it passes through this point. The other one we can obtain just by going to the blow-up coordinates. So the blow-up coordinates here are, well, alpha. So we should take, let me remember, what's better coordinate to take. Yes, so Q goes to PQ. Yes, so we have P1 Q1 plus gamma P1 square Q1 plus delta P1 equal to 0. So we can, so it is P1 times alpha Q1 plus gamma P1 Q1 plus delta. Yes, and it equal to 0. Well, so and we should pass through this point. Yes, so we obtain that this should be 0 in the point where Q1 is equal to A1 and P1 is equal to 0. Yes. So we have that delta equal to minus A1Q. So our pencil will be of the form alpha P. So it will be of the form PQ plus gamma over alpha Q minus A1. A1 alpha, sorry. A1 alpha. Yes. So our pencil will be of this form. And you see that gamma over alpha, the coefficient, is given by P, minus P plus A1 over Q. And you can ask, is this coefficient, why this coefficient is the same as this coefficient? That's not true, but they are related. It's simply to show that they are related by Möbius transformation. So the real coordinate transformation is P goes to minus P plus A1 over Q and some Möbius transformation of this. And for the variable Q, because H1 goes to H1, it's just some Möbius transformation. And we can, and now we should check that we can fix the Möbius transformation just by checking that here the blow-up is in the point 1, and so on. So when I'm preparing, I spent a lot of time to do this, but now we have no time for this. So you should believe me that after doing this, the answer will be as follows. Q goes to lambda Q, P goes to lambda P minus A1 over Q, P big, where lambda equal to plus minus 1. And T goes to lambda T, and A1 goes to minus A1, A2 goes to A1 plus A2, and A0 goes to A0 plus A1. So this variables is, due to this transformation, is called root variables, and they can be defined in another manner. So here we have in fact two transformations, not one, because here we have an obvious transformation. So let me remember the Hamiltonian. A1P minus A2Q. We can change the sign of P, Q, and T. Hamiltonian changes sign, and of course the Hamilton equations will be the same. Yes. So the extended canonical form will just change the sign. So and this represents this freedom. So if we take only transformations which preserve lambda, we will obtain such transformation. And you can check that this transformation is really a transformation of our symmetry of our Hamiltonian. So we have PQ minus T PQ minus A1 P minus A2Q, or maybe another direction, I think, or not. Let me check. Let me check. A1P minus A2Q. Yes, that's right. So we have that this goes to P minus A1 over Q minus T P minus A over 1 Q minus A1 P minus A1 over Q. Sorry. No, not A1, but plus. Yes, minus A2 plus A1 Q. So, and this should be the same. Is it visible? Let's see. Let's check this. Okay. So, so what we have? We have P minus Q minus T PQ. Yes. From here, and also we have three additional terms: minus A1 P minus A1 over Q. Yes, this is from here to here. Yes, here we have minus A1 P minus Q minus T. Yes. Here we have also plus A1 squared over Q.
How many times are you counting? Are you one time?
Because plus minus times minus. Why minus in the first term? Because here minus A1 over Q times this one. Minus A1P plus A1, plus A1P minus A1 square over Q, A1Q. So finally we obtain that this cancels. Also, let's see, this cancels. Yes. So this is a good term. This is a good term. And also here, in fact, this cancels with this. This is a good term. Sorry. Yes. I should not write this one, of course. Yes. You mean this? I should not write this term.
Like that, but why? I mean, you had P to transform in P minus A1.
Yes, but I divided first term in two and second term in two.
Yes, but then you have minus A1P, no? Which becomes plus A1P minus A1 Q.
So here I take P minus Q minus T times P, Q. Here I have minus A1 over Q times P. here I have p minus q minus t times.
Ah, you mean when you expand, you do not read. Ah, okay.
Well, so we have additional term only like a1t here, but it doesn't give anything to the equations. Moreover, I think that we can add. Yes. Moreover, we can, I don't know, maybe add something like a1t over half, and then we will have invariant Hamilton.
You shift it by a function of time, and this is
Yes.
So it's okay.
Yes, of course. Yes, of course, it's okay. So we see that, so we obtain some transformation, so in this transformation, I think, can be guessed, but maybe transformations which we will not discuss today, which are outer automorphism, cannot be guessed so simply. So the rotation can be guessed, but the reflection, no. So I think I should stop today.
Thank you.